All right, to finish off section 1.3, we're going to talk about spanning subgraphs and spanning trees. So a spanning subgraph of a graph G is a subgraph H of G such that H contains all of the vertices of G. So here we have a graph, right? And we can see that it has 5 vertices. And if we look at this subgraph, this cycle, right, around here, we can see that that subgraph contains all of the vertices. So we would say that H is a subgraph, spanning subgraph of G. Okay. All right. Similarly, a spanning tree of a graph G is a spanning subgraph of G that is a tree. Okay. So the H that we had on the previous slide is obviously not a tree, right? Because it contains a cycle, right? And so here I have an example of a spanning tree for this graph G. So you can see that that's spanning, this thing is a subgraph, right, of G, and it contains all of the vertices of G. So it's a tree. It contains no cycle. It's connected, right? So this is a spanning tree. All right. So the last result in this section that we want to talk about is that every connected graph contains a spanning tree. All right. How the proof of this goes, right, is that if I start with a connected graph G, right, it could be a tree. And if it is a tree, then we're done, right? So if G is a tree, we are done. Okay. If not, though, right? If G is not a tree, then G contains a cycle, right? All right, and so let E, I guess we should say let E1 be an edge on that cycle. All right, so let G1 be the graph that we get by taking the graph G and subtracting off the edge E1. All right, so we're deleting this edge. Okay, since it was on a cycle, G minus E1 is connected. Okay, and then if G1 happens to be a tree, we are done, right? Right, because G minus E1 still has all of the vertices of G. We didn't lose any vertices. We lost an edge, though, right? If not, right, then we repeat that same process, right? If G1 does not have, is not a tree, right, then it has a cycle. And so then it has an edge on that cycle. And so then we can look at another subgraph, G2. And that is going to be G1 minus edge 2. All right. And then we can keep playing this same game. All right. We do the same thing. We know that G2 is connected, right? because of the fact that we deleted an edge that came from a cycle, right? And we have that theorem that says that resulting graph is still connected. Okay, and if it's a tree, then we're good, right? If not, then it has a cycle, so it has an edge on it. We can delete that, and so on and so forth. Okay, all right. And so what ends up happening is that we will end up generating this sequence, right? G, G1, G2, right? G3, and so on and so forth, right? All of these are connected. Each one has one less edge than the one that came before it, right? So eventually what has to happen is that we will run out of edges, and so or cycles in there. This process cannot continue indefinitely. It must terminate, right, at some point. So at some point along the line, right, the one of these graphs, right, let's say G sub n, is a tree, okay? Because this process must stop, right? And it cannot, clearly, we cannot keep removing edges. If we ended up removing all of the edges, right, we will wind up with a graph that just has vertices in it, right? And that clearly is not connected, okay? So somewhere along the line here, one of these things must have had a, must have been a tree, okay? And so that's the proof that every connected graph, G contains a spanning tree.